Hi ladies and gentlemen, welcome back to my channel. Today we're gonna finish the tutorial on transformers. Now we're gonna do a few more things. Um, so let's just review what we had last time. We had a transformer, and on the primary side we have 12 volts. On the secondary side we have 120 volts, and we established then that this transformer is a step-up transformer. What happens here is you supply 12 volts through the transformer, and on the secondary the voltage increases by 10, which means the step-up factor is 10. Remember, primary turns ratio to the secondary turns will determine the step-up factor or step-down factor. So in this case you have 1 turn in the primary, you have um, 10 turns in the secondary, so the voltage will increase in that proportion. So also the current in the primary is 12 amps, and the current in the secondary is 10 times less, which is 1.2. And this is because I told you last time the power is conserved. You can see it here confirmed. So we're going to try again. Let's just start afresh. If you will, you can go to this website multisim.com and sign up and create your own circuits. It's free to sign up, and you can use some of their uh, free simulations. So let's just take it the transformer here. Well, this is 1:1. There's a center tap transformer. So let's just there's also one that is one primary, two secondary. In this case, we're just going to use one primary, one secondary. The things we need, obviously, you know this by now. We need a voltage source. We're going to use DC for now, just to demonstrate this theory, but we're going to use AC voltage ultimately at the end. Remember I told you guys last time, transformers allow AC currents to go through, but they block DC currents. So why do I use DC? Because this is going to give you almost like a static condition. It just does the math and tells you what is in and what is on the out. What we're going to do later, sorry, we're going to take a load first. Let's see these kinds of resistor, impedance block. Let's take an impedance block, right? Why not? Let's try the other one. Voltage controlled resistor. Now we're good with impedance block. So flip this guy around and connect. Most of your regular circuit we have some impedance, not just pure resistances, but you're gonna have complex impedances. So I think this is fair enough. We use this one here. Again, we're trying to measure the input and the output, right? So don't forget to put your ground. The reason being that our meter has a ground reference. Alright. I think that's all we need. Now let's run it down. Okay, so you can see 12 volts right here, 1.2 volts on the output, 120 microamps on the input, and 1.2 milliamps on the output. What does it tell you about the transformer? So it's not really the 1:1 that we thought it was, right? So let's see. You still think the transformer is a 1:1 after what we just saw? No, I don't think so. I think this transformer is 10:1. So we're gonna look at the characteristics of the transformer shortly. Just let's reconnect this ground. Let's reconnect the ground and see. Alright, always put your ground because the voltage meter has a ground reference. Now let's check the characteristics of this transformer, because what we saw doesn't agree with what we think. So primary turns is 10 and secondary turns is 1. Okay, so we just proved it, right? It's 10:1. Now we want to make the secondary higher to reverse the condition. So let's just make the secondary 100. So now the secondary is 10 times more. What that means then is the secondary voltage will also be 10 times more than the primary. So you have 12 volts here. We're going to predict 120 volts over there. Let's run the simulation one more time. All right, so you can see what I mean. But then the current is 10 times less, right? Just makes sense. Power is conserved. Whatever you put in, whatever power you put in, I squared R component of your input is also going to be your I squared R component of your output. And this Z is equal to A plus JB will be your impedance. Most practical loads we have the real parts and the complex parts. All right, so I think we're done here. We're just gonna try to use AC voltage as the source. This gives us a map of what it looks like, but if you look at a graph, what does the graph of what we just done look like? Just looks like a straight line 12 volts input, and then the output will be somewhere way above here, so we won't see that. So let's go back to the schematics and make a change. How about if we change the ratio so that we can do the change while it's running. So let's make this 12 is to 6, or 6 is to 12. Wait, let's make it 12 is to 6. Yeah, and so we can see it on the graph. Otherwise we're gonna adjust the graph. So without adjusting the graph, let's see if we can see both voltages. Yep. So when it's at 6 and when it's way down here 1.2 volts, and when it's at 12 volts, 12 volts, 1.2 volts. Okay, so that's the output. So this is 12 volts and this is 1.2 volts. The secondary is 1.2 volts. Let's play the screen and see both. The secondary is 1.2 way down here, and the primary is 12 volts. We did the adjustment so we can see the graph, otherwise we have to adjust the graph. Alright, but this is fine. Now the next thing we're going to do is to try using an AC voltage source, okay, because that's the practical application for transformers, is that your voltage source is AC, not DC. So let's put another voltage source, AC source. What do I have here? Sorry, AC current source, 90 and AC voltage source. So connect it as before, and then we're gonna run the simulation one more time. Alright, so that's it, and then we're gonna. So the frequency is so high, so why don't we adjust the frequency and the voltage? We adjust the frequency and the voltage. Right, so let's adjust the voltage. 1 volt, let's make it 10 volts. And how about the frequency? Let's make it a little bit lower. This is in kilohertz. Let's make it 1 per second. No, let's make it 10, about 50. Let's make it 50. This will be more 50 to 60 is fine, because that is more like what we see in the homes. Alright, now let's look at the graph. You can see the values fluctuate a lot, so it's really hard to tell what the value is. So if you go to the graph, you're going to see similar thing, right? So you're going to see the voltage is going, but you can look at the amplitude. So the amplitude at 10 and the other amplitude at around the 1 point something. Yeah, so let's see if we can get a single. Yeah, so right here you have one at around 10 volts, and the other one, the maximum amplitude is around 1 volt, right? So this is a plot. So this is the reality, what the graph is gonna look like. Let's see. Okay, let's make it automatic, not single. Go back to the schematics and the graph. We still frozen here. Normal. Okay, normal. Alright, so one more thing we're gonna do here with this is we're gonna try to rectify the output voltage and see what we get from there, right? So stop and start. So we're gonna rectify this voltage. Let's go to the schematics. And what do we learn about transformers? Transformers, um, voltage translators, if you will. They take input voltage and give you the same. If it's the same turns ratio, you get the same voltage and current and the output. But if there is any step up or step down function on the voltage, the reverse will be the case on the current. So when you have step up voltage, you have step down current. When you have step down voltage, you have step up current. So we are using an AC voltage source here, and then we've seen the signal is alternating on the output. Now we can rectify the output signal, and we can do voltage doubler, voltage quadrupler, and so on and so forth. Let's look at the parameters of this transformer. Stop. Input is 10, output is 1. So it's going to be a step down transformer. The voltage will be stepped down, but the current will be stepped up by 10. Now let's rectify the voltage, the output voltage, and see what it looks like. Okay, so we're going to remove this connection, and between that we're going to insert voltage rectifier. I don't think there's a voltage rectifier block here. Let's check one more time. General purpose. Okay, we don't see the voltage rectifier block, but it's not a problem. We're gonna make copies of this, but let's flip it around first and make copies so we can create a voltage rectifier. So there's full wave and there's half wave. So let's do half wave first. Half wave requires just one diode. Okay, I'm gonna use this one for that. Right, we're gonna keep these ones here. We're not gonna use them now. These are the ones we're gonna use them later. Right, let's plug it in here. For this we need an a capacitor. Alright, remember we discussed all these components. Now let's see them in action working together. And I'm gonna bring back this guy here. When you're rectifying the voltage source, make sure that the voltage of your capacitor is at least 4/3 multiplied by the value of your output voltage. So let's take this out. We're gonna put it back later. So 4/3 is like 1.33. So use 1.333 to multiply your output voltage. That will be the voltage of your capacitor. That's the rule of thumb. Okay, so we have the circuit set up the way we want it. Now let's connect this up, make a copy, and put another one here because we want to see how the waveform looks over there. Let's make a copy of this because we need one right here. Since we have some voltage meters on the output, we also need a ground reference. Now let's run this. We know we have, it's going to complain about the other components, but we're going to ignore them right now. It's okay, they are not connected. So let's look at the graph and see what it looks like. Oh, this looks ugly, but you can see what voltage is this. Dotted PR3. Let's see what is PR3. PR3 is the voltage going to the load. So it's rectified voltage this time around. Over here is still AC, but PR3 is a rectified voltage, but there's a lot of ripples on it, so we need to change the value of this capacitor. So let's do a split screen and see what happens as we change the value of the capacitor, shall we? Alright, let's change the value of the capacitor. And okay, so let's lower it a little bit. Alright, I'm gonna do a single now to capture it and see. Okay, we can't capture it from here. Alright, let's see. Why don't we remove all the other meters and see, because we still have two showing us. Let's make sure we have a step down transformer here. We still have step down transformer. So let's stop this and remove these other meters. Now we're just gonna have one meter here, the previous PR3, still PR3 right now, but you can see the, okay, let's let it go. So half-wave rectifier, what it does, it only rectifies one half of the voltage. So we are actually losing half of the voltage. You can see it goes, let's see if we can freeze it to see what's going on there. Let's go and graph, full graph, and see if we can freeze it. Freeze on single. Alright, you can see the falling edge and then the rising edge on the other side. Let's make it full wave so we can understand this properly. Sometimes you see the rising edge because it has to charge up the capacitor and then discharge. So we're losing half of the voltage. Now we're gonna go do full wave rectifier. I want to make sure this video doesn't take that long. So we have 18 minutes already recorded. So let's do full wave rectifier quickly. So to have a full wave rectifier, we need two diodes, and we're going to take each side of the transformer and connect it to this diode, to these diodes. So let's take we need to move this down here, and then the other one right under it. Doesn't have to be very pretty, so let's connect. Okay, and connect this transformer somewhere in between both of them, and then take the top, the positive side, to the load, and then take the negative side to the ground. Alright, and we're gonna check the voltage again. Alright, so something is missing, right? Full wave bridge, I need this component for. And then I need this one also. So this is the full wave bridge configuration. You have the half wave, and then you have the full wave, and there's also full wave two diodes, but in this case you're gonna use two capacitors. So in this case we're gonna just use one capacitor, and let's run this. All right, so let's see the graph. So the voltage is very low. um, Step down voltage. Let's stop it and go back to the schematic and change this, make it 1:1 so we can see what is happening. All right, let's see what is happening. Look at the graph. All right, so it's about 8 volts on the output, so we're losing about 1.6 volts. And do you know why that is? Let's go back here. Each diode will drop 0.6 to 0.7 volts in the forward direction. So you have 10 volts over here, 1:1 is 10. So you're going to lose 0.6 to this when it's positive going. At the same time, this is negative going. So you're losing 0.6 this way and 0.6 that way, or 0.7 this way, 0.7 that way. So 1.4 or 1.2 you're losing on each cycle. When this is negative going, you're going to lose 0.6, 0.7 here, and you're also going to lose 0.6, 0.7 over there. So D2 and D3 will conduct in one cycle, and D1 and D4 in the other cycle. So when it's positive going, D1 is conducting, also D4 is conducting in reverse direction. When this point is negative going, D2 is conducting, and the D3 is also conducting in the forward direction. So you're losing some voltage. That's why at the output you are getting 1.4 volts. You're losing 1.6. All right. So say these values, the calculation actually shows that we're losing about 1.6, which means 0.8 on each diode. And that's the reason when we stepped it down and made it 1 volt, you were getting almost 0. Why? Because you're dropping everything in the rectification, right? So let's just do quick step up transformer, right? Why not? So to do this step up, we can, or voltage doubler. Let's do voltage doubler. We still have 10 volts here. Let's see what we're going to see in the output when we do this voltage doubler. And to do a voltage doubler, the quickest one I did when I built amplifiers is to use 2 diodes and 2 capacitors, right? So this piece then will go to the top here. And then this piece will go to the middle here. Alright. So in this case, we're gonna get voltage doubler function. So let's make sure we put the meter in the right place. Okay, this is, I think this should be fine. So let's run it. Alright, so right here we have 10 volts, and over there we have about 18.2 volts. Again, we're losing the voltage doubler for this would have given us 20 volts, but we're losing about 2 volts. So we have doubled the voltage. As you can see that we almost double the voltage here just by using this configuration. 2 diodes and 2 capacitors in this configuration, we almost doubled the voltage. Let's change the value of this capacitor and make it, normally we use things like 450, 470 microfarad, 470 microfarad, and let's do the same over here. Right. So then the voltage, of course, make sure that the voltage it's at least 1.33 the value of the input voltage. So this is what you're seeing right here. When I say input voltage, I mean the voltage on the secondary side, right? Not necessarily the primary side. So we have shown this now. You can go ahead and do this if you want. You can build out this circuit and see how it functions. Another thing we're gonna do here is to let's just stop the simulation. Oh, look, sorry. Let's look at the graph. Right. Let's look at the graph and see the voltage is out of range, right? Because the meter we have, let's see, um, let's set the meter range, a maximum voltage. Let's make it 24 volts. Let's see, 24 volts. Yeah, let's run it again. We adjust the range to be able to see our voltage. You can see some ripples, right? It's not fully direct current, but the ripples is not that bad. So the value of your capacitor will determine the amount of ripples that you get. You can see it's ripple, it should be straight, but it's still fluctuating a little bit. But consider that value when it was 0 to 10, then back to 0, and then back to -10. So you can call this DC. They are all on the positive side and just a few ripples. We can increase this to 1,000 microfarad and say, or let's say 2,200. Let's do 4,700. 4,700. Yeah, how about that? How about that? The value will be more stable. The higher the value, 4,700 microfarad. You can see the ripples is less now. The fluctuations are less. So, yeah, the higher the value of your capacitor, the lower the ripples. It might not be very apparent here, but if we go down, let's go down. Why not? Let's make it 220 microfarads, right? 220 microfarads for each. You can see it's already running crazy. 220 microfarads. It's crazy, right? See the value? It's fluctuating a lot. So how about if you just make it 1 microfarad? That shouldn't happen. See the value? It's running all over the place. It's like you don't even have um, a filtering circuit at all, because your capacitor is supposed to filter out the ripples, and it's fluctuating all over the place, right? So you see the value of having a capacitor at the output. So it takes time to charge it takes a little time to charge the lower value capacitor, and takes little time also to discharge it. The higher the value, the more time it takes to charge it, and the more time it takes to discharge it. So the, the, the if the time it takes to charge and discharge is higher than the time is higher than your frequency, the time it takes to complete one cycle, then your filter, your ripple will be less. So the more the time it takes to discharge compared to your frequency, your ripple will be higher by that much. So let's say it takes 5 seconds to charge your capacitor, but you have, and it takes 5 seconds also to discharge it, but your frequency, the signal, the voltage goes through one cycle, maybe like 100 times in a second, 100 hertz, or maybe 50 hertz. Let's say 50 hertz or 60 hertz. Then the 60 hertz means 60 cycles in 1 second. Your capacitor is still trying to discharge when it has gone back to positive. So it rarely has time to go deep down, right? So it's about to go down, then it's already charging again, then it's about to go, it's already charging again. So it stays high. But if the time it takes to charge your capacitor is almost as the same, it takes to charge and discharge your capacitor is almost at the same as the frequency, or even less, then the function of the capacitor will not be noticed. You see the ripples, a lot of ripples, just like you see right now. So let's go back to reasonable value, 4,700. I could use a crazy amount of value here, but I want to use something in the realm of reality. It's been a long time I bought capacitors, so um, you could have 10,000 microfarads, but 4,700 does it for me. So let's try 10,000, right? Why not? This is free. This is free on the simulator, right? It's free, so you can just buy in quotes. So this is 10,000 microfarads, and you can see it's almost pure DC. It's pure DC basically. So if you want to try this, go ahead and do that. So the higher the value of your capacitor, the longer it takes to charge and discharge it. Remember, your Q is equal to IT. The charge is equal to current times time. So the current multiplied by the time is the charge you're pumping into it. And remember that the capacitance of a capacitor is constants of proportionality between the quantity of charge Q and potential difference V. So the your capacitance then is Q is equal to sorry, the C is equal to Q over V, and Q is IT. So CIT is equal to your V is equal to, so let's go through that again. So the C is equal to Q over V, the constant of proportionality between the quantity of charge Q and the potential difference V. When you cross multiply, V is equal to then Q over C, and Q is IT over C is your V. So the voltage you're pumping in multiplied by the time and the current, right, will give you the charge, the capacitance. So in this case, you have a very high capacitance, and you have the current is the same. We're not changing anything there. The voltage is the same. So the only thing we're changing is the capacitance, right? So the higher the capacitance, the more time it takes, right? So the higher the capacitance, the more time it takes to charge it. All right. So that's it for now. All right. So if you do that correlation, I'm just gonna zone this out. So I want you to internalize this formula. It's not really um, that complex, but I just want to make sure that it's communicated properly. So when you have C is equal to Q over V, and Q is IT, so the I and T are in the numerator of the V. If the V is constant, then for you to get a higher C, to charge higher C, you need to have more I and more T. It just, or more current or more time or more of both, right? So when the voltage is constant, in this case it is, the only thing changing is our C. So the higher the C, to get higher C from the same V in the denominator, then your I has to change, but I is not changing in our case. So the only thing that changes is the T. So you get higher T to charge. It takes higher time to charge and discharge the capacitor, right? That's why you see this almost like a straight line. Now, when we lower the value, just one more time, let's lower it by 10, each one by 10. When you lower it by 10, okay, it doesn't make much change. Let's lower it. Oh no, let's make it, we have 10,000. So let's make it 1,000 microfarads. As soon as you're making it 1,000 microfarads, you're noticing the difference right away. And the lesser you go, the so it takes less time this time to charge that. And remember, it takes time for the sinusoidal waves to go to complete cycle. So then it's coming down before you start charging again. So anyways, I think this is awesome simulator. So I'm going to end it here for transformers. If you have any question, please post your questions and comments. We're going to see how we can help. Try other forms of rectifiers, full wave, half wave, doublers, quadruplers, and so on and so forth. Pick up any architecture you like and just try it here, right? All right. Thank you. And when you do this, remember to put a load at the output. Otherwise, the value will be um, might not be the actual value on the output, right? So open circuit voltage is almost like infinity. It will just give any value. so you need to connect a load on it. All right, I'm gonna end this here on. So we didn't put a title to this, so why don't we put a title to it? This is our transformer. Alright, thanks for watching this. I'm gonna save this for another day. Save.